Today we're going to take a look at what we call the chain rule. So first, here are some of the derivative shortcuts we've learned so far: the power rule, the product rule, so if we have two functions multiplied, we can take the derivative, quotient rule that allows us to take the derivative if we have two functions being divided, and we have our trig functions that we can take the derivative of: sine, cosine, tangent, cosecant, secant, cotangent. But what we'll find throughout this course is a lot of the functions that we deal with are composed of two or more functions. So we need to figure out how to take the derivative when we have one function inside of another function. So first, here's some review of composite functions from pre-calc. So if we have the function f, which is, we're going to call it sine of x, we're going to let g equal x squared minus 3 root x plus 2. And we're going to take the composite f of g of x, and you can see the two different notations here that both represent the same thing. The idea here is to plug g of x into our function f. In other words, every time you see an x, replace it with the function g of x. So f of g of x, well, our outer function sine, and we plug g into x, and so we replace x with this whole long thing, x squared minus 3 root x plus 2. And we can go the other direction. We could have the function g of f of x. So we're going to plug f into the function g. And notice x shows up two different times in the function g of x. So we replace x with sine, that's sine squared x. And notice the notation here that it's common practice to bring the exponent inside the function. Minus 3 root x becomes minus 3 root sine of x. And then our plus 2 is still just plus 2. Let's go ahead and try one more. F is e to the power of x. G is tangent of x. F of g, so plug tangent into e, you get e to the power of tangent of x. G of f, you get tangent of e to the x. So let's say I give you a composite function, f of g of x, cosine of x squared minus 5. I want you to identify the functions f and g. So our outer function f is cosine, our inner function g is x squared minus 5. And here's just a quick question: is x squared sine of x a composite function? And the answer is no, it's a product of two functions. And that's really important to distinguish between the two because it's easy to get mixed up. All right, so now we're into calculus. We want to take the derivative of a composite function, f of g of x. And the derivative of f of g of x is f prime of g of x times g prime, meaning take the derivative of the outside, leave the inside alone, and multiply that by the derivative of the inside. So the chain rule comes in two forms, one using our function notation, another one using our dy dx notation. So dy dx equals dy du times du dx. So if we relate that back up to what we have up above there, dy du, that would be like f prime of g of x, and du dx would be the derivative of g of x. So u would be considered the inner function. In English, here's how we say the chain rule: take the derivative of the outer function, leave the inner function alone, then multiply by the derivative of the inner function. So start with the outside and then multiply by the derivative of the inside. So here's a function, sine of x squared minus 4. Find the derivative, and we want to evaluate it when x equals 2. So first, let's just try to find the derivative. The outer function is sine, the inner function is x squared minus 4. The derivative of sine is cosine, leave x squared minus 4 alone. And we're going to multiply this by the derivative of the inner function, x squared minus 4, which is 2x. So that's our derivative. We can evaluate this when x equals 2 by plugging in 2 for x, and it becomes 4. All right, derivative of secant to the fifth might help to rewrite this as secant of x all to the power of 5. That helps you to realize that the exponent of 5 is the outer function, and secant is the inner function. So the 5 comes down, becomes a 4, the secant stays the same, multiplied by the derivative of secant, which is secant tan. And we can simplify this because we have secant to the 4th times secant, that's secant to the 5th. Cosine squared of 3 of x. So again, we can rewrite it with the square on the outside. Bring the 2 down, leave the cosine alone. Now we take the derivative of cosine of 3x, and we should notice that here, we're going to have to use chain rule again, because we again have a composite function. So leave the 2 cosine of 3x alone. Derivative of cosine is negative sine. Leave the 3x alone, and we multiply that by the derivative of 3x. So we just keep working from the outside in, and we can do this as many times as we need to, which is why we call it the chain rule. All right, and just to point out, every problem technically could be thought of as a chain rule problem. Even if we take the derivative of x squared, that's 2x times the derivative of the inner function x with respect to x. Well, the derivative of x with respect to x is just 1, so we still just get 2x. So not something you have to do in practice, but just pointing out that the chain rule really is used all the time. All right, and one last example here. Let's say we have y equals u cubed plus 1, and u equals sine of x. We want to find dy dx. So here's our chain rule, and notice that we have this second form of the chain rule, which we haven't really used up to this point. So let's go ahead and try that. dy du is 3u squared, and du dx is cosine of x. So dy dx is 3u squared cosine of x, but that's kind of weird because we have a u and an x, but look up above, and we know that u equals sine of x. So 3 sine squared times cosine. And you can see that this really is the same thing as f of g of x. Our original function, if we actually put this all together, would be y equals sine cubed of x plus 1, and we could have used that upper rule as well. It would result in the exact same thing.